Welcome to this comprehensive scientific lecture on how temperature and time affect the properties of meat during cooking. We'll explore the biochemical and physical transformations that occur at different temperatures and durations. Let's begin by asking a fundamental question. Why does cooking change meat at all? Meat is primarily composed of proteins, water, and fats. These components undergo dramatic transformations when exposed to heat. Proteins denature and coagulate when heated. This means their three-dimensional structure unfolds and then reforms into new structures. Water evaporates from the meat, fats render or melt out, and collagen, the connective tissue, breaks down into gelatin. Here we see the structure of raw meat. The red circles represent protein fibers, and the blue lines represent water molecules trapped within the muscle structure. There are several critical temperature zones that trigger specific changes in meat. Let's explore each one systematically. At 40 degrees Celsius, we are in what food scientists call the danger zone. But what happens at this temperature? 40 degrees Celsius is too low for proper cooking. This temperature is barely above body temperature. Bacteria multiply rapidly between 4 and 60 degrees Celsius. At 40 degrees, we're right in the optimal range for bacterial growth. No significant protein denaturation occurs at this temperature. The meat remains essentially raw in structure. Here's a table showing cooking times at 40 degrees Celsius. Notice that all durations are unsafe. Even 30 minutes at this temperature allows dangerous bacterial proliferation. At 60 degrees Celsius, we begin to see the first real transformations in meat structure. Myosin proteins, one of the major muscle proteins, begin to denature around 50 to 55 degrees Celsius. The meat begins to firm up and turn opaque as proteins coagulate. However, it's still quite soft and undercooked. Most pathogenic bacteria are killed above 60 degrees Celsius, making this the minimum safe internal temperature for extended cooking. This table shows how time at 60 degrees affects meat. Shorter times give a very rare texture. Longer times allow pasteurization, where the combination of time and temperature kills bacteria. At 80 degrees Celsius, we see much more rapid transformations in meat structure. Actin proteins, another major component of muscle, denature between 66 and 73 degrees Celsius. Significant water loss begins at this temperature. The meat contracts and squeezes out moisture. Collagen, the connective tissue, begins its slow conversion to gelatin, though this process takes many hours. Water loss is proportional to both temperature and time. Higher temperatures accelerate moisture loss. Here's what happens at 80 degrees over time. After 30 minutes, you get a medium doneness. After an hour, the meat is well done. Beyond 2 hours, the meat becomes increasingly dry as water continues to evaporate. At 100 degrees Celsius, we reach the boiling point of water. This creates unique conditions for meat cooking. Let me pose a question. What happens to meat when cooked at the boiling point of water for extended periods? First, rapid water evaporation occurs. The meat can lose 30 to 40% of its weight in water. All muscle proteins are fully denatured within minutes at this temperature. Collagen breakdown accelerates significantly. At 100 degrees, collagen converts to gelatin much faster than at lower temperatures. This diagram compares meat cooked at 100 degrees for short versus long periods. Short cooking produces firm, dry meat. Long cooking, despite continued water loss, produces tender meat as collagen fully breaks down. At 120 degrees Celsius, we're above the normal boiling point of water. This requires pressure cooking or specialized equipment. This temperature is achieved through pressure cooking, where increased pressure raises the boiling point of water. The Maillard reactions, which create complex flavors and brown colors, begin to occur around 120 to 140 degrees Celsius. Collagen breakdown becomes very rapid at this temperature. Tough cuts can become tender in 1 to 2 hours. The time required for collagen breakdown at 120 degrees is approximately 1/4 of the time needed at 100 degrees. This table shows collagen breakdown at 120 degrees. Notice how quickly tenderness develops. After 3 hours, the meat can actually become mushy as the structure completely breaks down. At 140 degrees Celsius, we enter the realm of dry heat cooking methods like roasting and baking. In a standard oven, the surface of meat reaches this temperature while the interior remains cooler. Maillard reactions are very active at 140 degrees. creating the characteristic browned, flavorful crust on roasted meats. The surface dries rapidly and forms a crust. This crust helps retain moisture in the interior of the meat. This cross-section shows a roast at 140 degrees oven temperature. The outer layer reaches high temperature and forms a crust, while the interior remains at a lower temperature and retains moisture. At 160 degrees Celsius, we're at a common roasting temperature that balances cooking speed with quality. Let's ask, why is 160 degrees Celsius such a popular temperature for roasting meats? It balances cooking time and moisture retention. Higher temperatures cook faster but dry out meat more. Lower temperatures retain moisture but take longer. This temperature develops a good crust without burning the surface. The majored reactions proceed at an optimal rate. It allows even cooking of large roasts. The heat has time to penetrate to the center without overcooking the exterior. This table compares cooking times for different sized roasts at 160 degrees. Notice how a larger roast requires proportionally more time for the heat to reach the center. At 180 degrees Celsius, we're using a faster roasting method that creates excellent crust development. Faster cooking with enhanced browning occurs at this temperature. The Maillard reactions accelerate significantly. There's a risk that the exterior dries out before the interior cooks properly, especially with thick cuts. This temperature is ideal for smaller cuts and poultry, where the ratio of surface area to volume is higher. The thickness of the crust is proportional to the square root of cooking time. Longer cooking creates a thicker, darker crust. This comparison shows why cooking time at 180 degrees must be matched to the meat type. Chicken is perfect at 1 hour, but beef needs longer. Beyond optimal times, quality deteriorates rapidly. At 200 degrees Celsius, we're entering high-temperature roasting territory. This creates dramatic transformations. Very rapid surface browning occurs within the first 15 to 20 minutes of cooking. Significant moisture loss from the surface happens quickly. The exterior can become quite dry. The interior can remain underdone if cooking time isn't sufficient. There's a large temperature gradient from surface to center. This diagram shows the temperature gradient in meat cooked at 200 degrees for a short time. The surface is very hot and dark, while the center remains cool and pink. At 220 degrees Celsius, we're at the upper limit of conventional oven cooking. This is extremely aggressive heating. This temperature is typically used for initial searing to develop crust quickly, or for very small cuts that cook rapidly. There's significant risk of burning and developing acrid, bitter flavors if meat is left too long. This temperature creates maximum Maillard reaction products, giving intense flavors when used correctly. This table shows safe usage times at 220 degrees. Only 10 to 15 minutes is appropriate for searing. Longer times result in burnt, inedible meat. Now let's explore in detail the science of collagen breakdown, which is crucial for understanding long cooking times. Collagen is a triple helix protein structure that provides mechanical strength to connective tissue in meat. When heated in the presence of moisture, collagen hydrolyzes and converts to gelatin, a much softer substance. This conversion requires both adequate temperature and sufficient time. Temperature alone isn't enough. The rate of collagen breakdown follows the Arrhenius equation. K is the rate constant, A is a frequency factor, EA is activation energy, R is the gas constant, and T is absolute temperature. Let's ask a critical question. How exactly does temperature affect the rate of collagen breakdown? As a rule of thumb, the rate of collagen breakdown approximately doubles for every 10 degrees Celsius increase in temperature. For example, the time required at 80 degrees is approximately 8 times the time required at 120 degrees for the same degree of collagen breakdown. This table quantifies collagen breakdown times. At 60 degrees, it takes 24 hours. At 120 degrees, only 1 hour is needed for the same result. Notice the exponential relationship. Now let's examine practical cooking scenarios, combining different temperatures and times. First scenario, cooking a tough cut like beef chuck at 80 degrees Celsius for 8 hours. The low temperature preserves moisture well. Water loss is minimized compared to higher temperatures. The long time allows complete collagen breakdown, transforming tough connective tissue into tender gelatin. The result is very tender, moist meat with a soft texture. This is the principle behind sous-vide cooking. Second scenario, Cooking a lean cut like beef tenderloin at 180 degrees Celsius for 1 hour. The high temperature creates an excellent crust through Maillard reactions and caramelization. The relatively short time prevents excessive drying of this already lean cut. The result is a well-browned exterior with a pink, juicy interior, perfect for steaks and premium cuts. Third scenario. Roasting a whole chicken at 160 degrees Celsius for 2 hours. The moderate temperature allows heat to penetrate evenly from the surface to the bone. 2 hours is sufficient for the thickest parts to reach safe internal temperatures above 75 degrees Celsius. The result is golden, crispy skin with moist, fully cooked meat throughout, including at the bone. This diagram summarizes our 3 scenarios. Each represents a different strategy. Low and slow for tough cuts, hot and fast for premium cuts, and moderate for whole birds. Let's examine the relationship between water loss and final meat texture across different cooking regimes. Raw meat contains approximately 70 to 75% water by weight. This water is held within and between muscle fibers. Typical cooking causes 20 to 40% weight loss, almost entirely from water evaporation. Moisture loss is a function of temperature, time, and the humidity of the cooking environment. This table compares water loss across different cooking methods. Notice that sous-vide at low temperature has minimal loss, while high-temperature roasting loses the most water. Now let's discuss the role of fat in marbling, and how they interact with our temperature and time parameters. Intramuscular fat, or marbling, begins to melt at 40 to 50 degrees Celsius for beef. As fat melts, it lubricates the meat fibers, contributing to the perception of tenderness and juiciness. At higher temperatures, fat doesn't just melt, it renders out of the meat completely, potentially leading to dryness despite the fat content. This comparison shows well-marbled meat on the left, with yellow fat deposits, versus a lean cut on the right. The marbled meat is more forgiving of longer cooking times. Here's a practical question. What are the ideal internal temperatures for different levels of doneness? Rare beef is cooked to an internal temperature of 50 to 52 degrees Celsius. The center is cool and red. Medium rare is 55 to 57 degrees. This is warm and red in the center. Medium doneness is 60 to 63 degrees. The center is pink and hot throughout. Medium well is 65 to 68 degrees. Only a slight hint of pink remains. Well done is 71 degrees Celsius and above. The meat is uniformly brown throughout with no pink. This gradient shows the color progression from rare at the top to well done at the bottom. Each level corresponds to specific internal temperatures and protein denaturation states. Let's discuss an advanced concept, carryover cooking. This is crucial for understanding the relationship between oven temperature and final doneness. Meat continues cooking after removal from heat due to residual thermal energy in the outer layers. Internal temperature typically rises 3 to 10 degrees Celsius during resting, depending on the size and cooking temperature. Larger roasts have more carryover because they have greater thermal mass and more stored heat. The carryover temperature increase is proportional to the mass to the 2/3 power, relating to the surface area to volume ratio. This table shows carryover cooking for different sizes and temperatures. Notice that larger roasts at lower temperatures have the most carryover. You must remove them from heat before they reach target temperature. Now let's do a comprehensive analysis of specific time-temperature combinations and their effects. First, let's consider what happens with just 30 minutes of cooking at different temperatures. This table analyzes 30-minute cooking across temperatures. At low temperatures, 30 minutes isn't enough. At moderate temperatures, like 180 degrees, it's perfect for steaks. At 220, it's only for searing. Now let's examine 1 hour of cooking time across our temperature range. After 1 hour, we see clear differentiation. Low temperatures produce rare meat. Moderate temperatures give medium to well done, and high temperatures risk burning. At 3 hours, we're entering the territory of braises, roasts, and low and slow cooking. Let's see what happens. At 60 degrees for 3 hours, tough cuts begin to tenderize as collagen slowly breaks down while retaining maximum moisture. At 100 degrees for 3 hours, you achieve excellent results for braising. Collagen is mostly converted, meat is tender. At 140 degrees and above for 3 hours, there's significant risk of excessive drying unless the meat is submerged in liquid. This table quantifies 3-hour cooking results. Notice the inverse relationship between temperature and moisture retention. Lower temperatures preserve more moisture while still breaking down collagen. Finally, let's examine ultra-long cooking times of 6 to 8 hours. These are used for specific applications. At 60 degrees for 6 to 8 hours, you achieve sous-vide perfection. Even the toughest cuts become fork tender while remaining perfectly medium rare. At 80 to 100 degrees for 6 to 8 hours, you get traditional slow cooker results. Excellent for stews and pulled meats. Above 120 degrees for this duration is generally not recommended. The meat becomes extremely dry and can develop off flavors. This matrix shows quality outcomes for long cooking times. Lower temperatures maintain quality even at 8 hours, while high temperatures fail. Let's address another important question. Why does meat need to rest after cooking, and for how long? Resting allows juices to redistribute throughout the meat. During cooking, liquids are driven toward the center by heat. As the meat cools slightly, muscle fibers relax and can reabsorb some of the expelled moisture. Resting time should be 5 minutes for small cuts like steaks, up to 30 minutes for large roasts. A good rule of thumb is that rest time should be approximately 1/10 of the cooking time, with a minimum of 5 minutes. Let's work through a comprehensive practical example, combining everything we've learned. We have a 2-kilogram beef brisket, which is a tough cut with significant connective tissue. What's the optimal cooking strategy? Option A. Cook at 200 degrees for 2 hours. This will give a good crust, but the interior will be tough because collagen hasn't fully broken down. Option B. Cook at 80 degrees for 8 hours. This will result in complete collagen breakdown with maximum moisture retention, but no crust. Option C. Start at 220 degrees for 20 minutes to develop crust, then reduce to 100 degrees for 5 hours. This combines the benefits of both approaches. This diagram compares the 3 options. Option C combines the best of both worlds. Initial high heat for crust development, followed by long, low cooking for tenderness. Let's summarize the key scientific principles we've covered in this lecture. Protein denaturation, the unfolding and coagulation of muscle proteins, occurs between 50 and 75 degrees Celsius. Collagen conversion to gelatin requires both adequate heat and sufficient time, following exponential kinetics. Water loss increases with both temperature and time, but temperature has a more dramatic effect. Maillard reactions, which create flavor and color, require temperatures above 120 degrees Celsius to proceed at appreciable rates. This table summarizes the key processes and their temperature and time requirements. Notice how different transformations occur at different temperatures and timescales. Based on all this science, here are my final recommendations for different cooking scenarios. For tender cuts like steaks and chops, use high heat between 180 and 220 degrees for short times of 20 to 60 minutes. For tough cuts with lots of connective tissue, use low heat between 80 and 100 degrees for long times of 3 to 8 hours. For whole birds, use moderate heat around 160 to 180 degrees for moderate times of 1 to 3 hours depending on size. For maximum quality on tough cuts, use combination methods, high heat first for crust, then low heat for tenderness. This chart shows recommended time-temperature combinations for different cuts and methods. Each represents an optimized approach for that specific application. In conclusion, cooking meat is where art meets science. Understanding the underlying physical and chemical processes allows you to make informed decisions. Temperature determines the rate at which chemical and physical changes occur in meat. Time determines the extent or completeness of those changes. Optimal results require carefully matching your cooking method to the specific characteristics of your meat. Thank you for joining this detailed scientific exploration of how temperature and time influence meat cooking. Apply these principles in your own cooking to achieve consistently excellent results.